Okay, back. This is the third lecture for chapters 7 through 9, and we're getting into populations. This curve here shows a little bit of the potential difference we could have between exponential and logistic growth models. So looking at this first part of the curve before I put any notes in here, they put both of them kind of together here. We have this biotic potential, which typically is talking about our selected species. Biotic potential. So these species are, taking off and they're exploding. So initially, think of the bacteria with potato salad. If it's in the refrigerator, you don't have any growth going on. But once you put them out on that hot August day, the conditions are right, so that they take off. And eventually they get to a point, so this may not be the best example here, but eventually you get to a point where they will level off based on some environmental factors that will hold them there, not for the bacteria. I apologize for that. But for K-selected species, they typically will find a balance. What is the carrying capacity? And they will be limited there. So this environmental resistance holds them. So for our selected species, we aren't going to see this top portion up here. This limits. For K-selected species, they have a limit in which they come to. So the differences between these curves, just kind of drawing it out here, is for our selected species, what I'm looking at is just an exponential curve. If it's a K-selected species, you still have that exponential growth, but you have a leveling off point. So we'll make a comparison with those a little bit more as we're moving along. The names for these is the J-shaped curve would be for the R-selected species, having that exponential growth, and the S-shaped curves would be for K-selected species. But they both do have an exponential portion, that rapid growth rate. The difference is for R-selected, it doesn't level off. Eventually, it will just crash. Okay. So, little calculation here. Population has a growth rate going from 100 individuals to 105. So there's some births, there's some deaths, there's some immigration, but ultimately after 1 year, our population has changed to 105 from an original 5. So we want to know what the population growth is and what would be the doubling time. Okay. So taking a look first, I already put the answer in there. Taking a look at the first part here as far as figuring out what would my growth rate be, we would either have to do some subtraction or we could figure out that my change in population was 5. And I'm going to divide that by 100, which is my original population, and then multiply times 100% just so I can get it to a growth change potential. So that turns into my growth rate for the year is 5%. Now to figure out the doubling time, we're going to take 70, as you can see here, take 70 and divide that by my growth rate, rule of 70, and that'll give me 14 years. So a nice simple way. So you should be familiar with these. I think we'll see one of these on the exam. And another equation that is out there, we're not going to use it, but it kind of will go on along with the same scenario, is this equation here, and this is representative for R selected species. So this is the definition of biotic potential. You'll want to hold on to that information. So R selected species have biotic potential. So just based on their growth rate, this is what they're going to do. Another way of seeing this equation, which I've seen in some resources, is using the integrated form, I believe. I remember that little portion of calculus is using d, or small case d, in comparison or instead of the delta symbol. But the rest of the equation would be the same. And again, this is for biotic potential. Okay, so here is an actual the actual equation which we can look at for exponential growth, and we'll look at some of the variables that go into this equation, and we'll do a quick little math problem here with bunnies. So let's just say we start off with 10 bunnies. And we know that we have a growth rate of 0.5 or 50%. We want to know, and this is the growth rate per year, how many bunnies will there be in 5 years, or 1 year, or 10 years? So we have to put all these little variables into an equation. So the number of bunnies we originally have is 10. And we're talking about e. So if we look at our calculator, it's probably the second function for natural log. So we'll put the e function in. And our growth rate is going to be 0.5. And that's an exponent. And for 1 year, fine, we'll just put that in there. And our answer will be somewhere about 16, 16.4, something like that. And then we just keep moving along. The only change we're going to make here is instead of using 1, we'll substitute a 5 in there and substitute a 10 in there and see what your numbers come out to be. So it's pretty interesting when you actually can look at it from this format, is you see how much the numbers will actually go up. So we'll go up to 122 after 5 years of these rabbits. So remember, I originally had 10. 5 years later, I got 120. And 10 years later, we've got that many rabbits running around. So rabbits are very much considered to be an R-selected species. Okay, well, that's not a guarantee that you're going to have that many rabbits running around. So what actually can happen? Well, let's just pretend our little rabbits are doing their thing, and eventually their numbers get really, really high. Yeah, I know they got reindeer here. Well, there's only so many resources to go around. So eventually something's going to put them back in check, and the population will have what's called a die-off. So it comes back to what we know the population sustainably can be. So put the rabbits out because they're an R-selected species. This one will work a lot better because it's a K-selected. And we can generally say, look, this is what reindeer population should be. They should be in this range. So we see the numbers going up, as we're seeing here for some reason. Maybe a predator has been removed from the ecosystem. We can see that, okay, something is not right. Something needs to correct itself. So potentially, let's just say, for example, we removed wolves, and the population had always been in this little area here, and wolves have been removed. Well, fine, we can have a population up to here, but then something else in the environment will create what we can say a new carrying capacity, and maybe it stays at that limit. Example, deer in Michigan. As I mentioned real early in the lecture, the population we have for deer today is much higher than it was back in, say, early American or colonial days. Just a couple definitions to take a look at here. The difference between population size and population density is just the very small difference of defining per unit area. So we can say in Southeast Michigan we have, just making it up, 5,000 deer. Okay, that's the population size of the deer in Southeast Michigan. But if I want to say the density of the deer in Southeast Michigan, I would have to say 5,000 deer per 10,000 square miles. That would be a density. So a very, very small difference between the two, but density has a unit. Predator-prey interactions. This one here, just take a look at the differences in the lines you have. You have the lynx and the hare. Lynx being, of course, this guy here. Looks more like a teddy bear attacking a rabbit. Okay. But what we will notice is as the hare population starts to spike, just behind it, you're going to have the lynx population spiking. And then once the hare population falls, the links population will follow. So that's the pattern we need to be aware of here, is which one goes up first and which one will follow. So take a look at those differences. All right, we'll take a break here. This is the end of the third lecture, and we'll finish it off with starting with metapopulations.